All right, good morning, everyone. Welcome to day 2 of the data analysis in our workshop. I hope everyone has had a chance to get a little bit of caffeine this morning. Before we get started, I just wanted to again mention the materials page of the website. So the recordings from yesterday's session are all available now. If you hit the recording button, it'll take you right to the section of the video where we started that session. And the materials for today have also been posted. So you can find those slides and copies of the exercises on the website as well. All right, so when we left off yesterday, we had been looking at a graph that looks like this. So this was the graph for my name. I'm looking at how the proportion of children with the name Jake changed over the years in our baby names data set. And so this is like one way you could think about this is the popularity of the name Jake across the years. And so what we want to do now is think about which name is the most popular, or which names plural have been the most popular. And so there are a couple things we have to do first, which is one, figure out what we mean by popularity. So there are a couple ways we can do this. The first is through just a count, like how many children have had a name across all of the years. So that's one way we could do this. Another way is we could look at ranks. So we could look at whether a name ranks among the top names from year to year. And so this might be helpful if there are large changes in the population size over year. So for example, names that were very popular in the 1800s might not show as popular overall when we look at just the sums, because there were fewer children born there. So our using the sums, our measure of popularity would be more heavily weighted toward years when a lot of children were born. So looking at ranks could help us account for that. So getting us all thinking early in the morning, do we have enough information in our baby names data set? And feel free to pull that up in your R project, take a look and remind yourself what variables are in there to calculate the total number of children with each name, or also to rank the names within each year. So I'm going to say that yes, we do have the information we need to do this. We just need some new functions from dplyr, and that's what we're going to talk about this morning. So these are functions that I would put under like the deriving information sort of label. So the first one we're going to look at is summarize. So that's going to look at how we can take all of our data set and get just a few summary statistics out of it. Then we'll look at group by, which is really just used for analyzing groups within your data set. So you can say like these rows go together, and these rows go together. And then the last one we'll look at is mutate, which is for making new variables in your data. So we're going to start with summarize. So just like the other dplyr functions that we've looked at so far, the summarize function works by taking a data frame and then telling it how you want to summarize the data. So again, that first argument is going to be the data frame. So it works with the pipe. And then we tell it which summaries to calculate. So if we take the baby names data and we say summarize this data, and I want two summaries. I want the total, which is going to be the sum of the n. So that'll give us the total number of children in our data set. And then we can say, I want the max n. So that's the highest n count in that n column. And when we do that, we see we get those two summaries back. So we get the sum of N, which is like 348 million-ish. And then we see that the highest N that we have is just under 100,000. So there are a lot of summary helpers and summary functions. These are listed in the dplyr cheat sheet. So you can look at N, which is like the number of values or rows. N distinct will give you the number of unique values. Then there's the more standard things you might think of as summary statistics, like mean, median, standard deviations, all those sorts of things are in there as well. All right, so now in your exercise, our markdown file, we want to use summarize to compute 3 statistics about our baby names data. We first want to find the first year in the data, so that'd be the minimum year, the last year in the data, which would be the maximum year, and then the total number of unique names in the data. And then I give you a hint on which functions those should be. So we'll give just a few minutes to work on those summaries, and then we'll come look at the answers. All right, so let's see what we have going on. How is my font size? Do I need to zoom in a little bit more? All right, I'm going to assume it's good, but if I need to zoom in, let me know. All right, so we start with the baby names. And then we want to summarize. And we can say that the first year is going to be the minimum of the year variable. The last year is going to be the max year, so that'll be the highest year in our data set. And then the total number of names will be indistinct, so that's the number of distinct values of the name variable. And so if we run that, we see we get our 3 summary statistics. So the first year was 1880, the last year in the data is 2017, and we have just over 97,000 names in our data set. And these can be named whatever you want. So I've called them first year, last year, but if you wanted to call this like the minimum year, you can do that, and that'll just be what the new variable is called in your summary. All right. So now we're going to combine some of the stuff we did yesterday with the summary function. So what I want you to do now is to first filter the data so that it only has kids named Khaleesi, and then use the summarize function to find the first year that Khaleesi appeared in the data. All right. Amber, I was trying to react to your message in the chat, but apparently Zoom doesn't have that capability. Or at least I am not smart enough to figure it out. But yes, this is a lot of information that I'll be throwing at you all over yesterday and the rest of this week. So I think it is perfectly normal to be forgetting what all we did yesterday.
Yeah, just a little slow to start, I think.
It's also very early in the morning, so we're still waking up.
Well, I don't have that excuse. I'm on the East Coast, so.
Oh, okay, well, you're an hour ahead of us, so. All right. So to do this, we're going to start with the baby names data. And we will first, we want to extract only the rows that have Khaleesi, so we'll use filter for that. So we'll say filter to only places where the name is equal to Khaleesi. And so if we look at just that, we can see we have just those rows. And this is a case where maybe we don't actually need summarize because there's only 7 rows. We can see that the first year is 2011. But just to complete it, we can then say summarize. And then the first year is the minimum of the year variable. And so we see that the first year that this name appeared in our data was 2011. All right, was everyone able to get that? Awesome. All right. All right, so now we're going to talk about group by. So as I mentioned earlier, group by is a function for grouping your data. So just like all of the other dplyr functions and almost all the functions in the tidyverse in general, the first argument is going to be that data frame that you send into it. So it works with the pipe. And then you specify the variables that you want to group by. And so when you use group by, it actually doesn't look like it does that much to your data. So here we do group bys or group by, and we say we want to group baby names by the sex variable. And so at first glance, it does not look like anything has changed. We still have all of our rows, all the columns look the same, but now we have this extra line at the top and this metadata for our data frame that says there are 2 groups. It's grouped by sex and there are 2 groups. So what can that do for us? Like this doesn't really do anything on its own. But what groups allow us to do is grouped summaries. So we can take the baby names, group it by sex, and then when we use summarize, so if we do the number of distinct names, now instead of 1 overall count, we get a count for each of the groups in our data. So we can say there are 67,000 unique names for females and almost 41,000 unique names for males in our data set. So group by doesn't do a whole lot on its own, but it lets us do more things with our other functions like summarize. All right, so now we're going to play with group by a little bit. What I would like everyone to do is to calculate the popularity of different names by determining the total number of children that have been given each name. So I've laid out a few steps here. First, we want to use group by and summarize to calculate the total number of children that have been given each name by sex, and then arrange the results to show the most popular names first. And then if you want to go crazy, you can then take that and create a bar plot of the 10 most popular names with name on the x-axis and total children on the y-axis. All right, so we'll take a few minutes to work through this, and then we'll come back and see which names are the most popular. All right. Okay, so first we want to calculate the popularity of our names. Quick question in the chat. How to bring up our data set so we can see the variable names. Yes, so in your console, if you just type in the name of the data set, so here's baby names, it will show you your data in the console. Another way to do this that is handy if you have a large data set with more than like this is nice because it fits all like in your console, but if you have a lot of variables, this might be messy to look at. There's a function in R called call names. So call short for column, names, and then baby names. So this would be the name of your data set. And then it'll show you just the variable names from your data. All right, so to start, we're going to take the baby names. And we want to know the total number of children that have been given each name. So we're going to group by name, and we'll also group by sex. And then we will summarize. And so say the total number of children that got each name is just going to be the sum of that in column. So if we look at just those results, we now see for each name, the total number of children that have gotten that name across all of the years in our data set, broken down by sex. So now we want to see the most popular names. So we can take this result and we want to arrange. And we want the highest numbers at the top. So we will do by descending order the total variable that we just created. So if we run this code, we now see that the most popular names, just by the raw number of children, James, John, Robert, Michael, these would be what we'd say the most popular in terms of the number of children that have gotten those names. Does this make sense how we go about combining all of these different functions? All right, I will assume silence means yes, unless I hear otherwise. All right. And so then if we wanted to make that bar graph that visualize that data, there's a new function here that I have not talked about. This is a good example of like dplyr and the tidyverse are like very large functions or packages, and we're not going to be able to talk about everything that is in them. So there are things that they will do that we won't talk about explicitly, but I will try and sprinkle some in as I'm able to. This one is called slice max, and so it will take the like top however many rows you want. That's what the max is. So it says from this data, I want the top 10 rows by total. So give me the 10 rows that have the highest value of total. And then we create our ggplot. And so this is code that hopefully looks familiar from yesterday. We're putting the total on we're putting the name on the x-axis. This factory order function is one that we're going to talk about later today. So you'll get to learn about factors and how to manipulate those. And then on the y value, we want the total number of children. And so if we look at that plot, we now have a bar graph that shows for the top 10 names, how many children have received that name over all of the years in our data. All right. So now, what I'd like you to do is use our grouping and the functions we've learned so far to calculate the total number of children born in each year, and then plot the results as a line graph. So we're basically wanting to make kind of like a population curve showing the number of children that are born in each year and how that changes over time. All right, so how do we want to tackle this one? The way that I think about like figuring out what to group by is thinking about like what I want my data set to look like at the end. So I know that what I want is a line graph with the total on the Y and the year on the X. So I think what I want my data frame to look like is one row per year with the total number of kids in the next column. So since I want one row per year, that tells me that I should group by the year variable. So we start with baby names. We're going to group by year. And then we will summarize and say that the total number of children is going to be equal to the sum of the n column. And so if we run that, we now see one row per year, as we were expecting, and we get the total number of children that were born in each year. So now we can send that to ggplot. So again, we can just pipe ggplot. We want to map our x-axis to the year, our y-axis to the number of children. And then we want to add a geom line. So if we run all of that, we now have a graph that's showing us the number of children that were born in each year in the United States. And so if you are familiar with US history, you recognize that this is the baby boom. And so this makes sense with what I would expect given what we know about history here. All right, was everyone able to get that graph?
Jake? So for my summarize, I did total equals sum of n. Is that just it appears to have gotten the same numbers? Is that another option or is that
Yeah,
automatic?
yeah, for sure. So you can name this variable whatever you
Oh, I
want to.
see.
Yeah, so
Yeah.
like I could name this like apples if I really wanted to. Like the only thing you have to make sure is like then this in children doesn't exist in the data anymore. So then I have to call this apples, but then it'll do the exact same thing. So yeah, you can
Okay.
name this whatever you want.
All right, that helps. Thank you.
Yeah. All right. All right, so now we're going to move on to mutate, which is the last of our kind of deriving information functions. So again, mutate's going to work just like all of the other functions from dplyr. It's going to take that data frame first, so it'll work just perfectly with the pipe. And then the additional things we're going to add are the new variables that we want to calculate. So for example, if we start with our baby names data and we want to mutate it, we can make a new variable called %, which is going to be the prop variable times 100. And then there's a function called round. And so we can round this to 2 digits. And then that will give us a new variable called %, which is prop times 100, all rounded to 2 digits. And again, this, like the name of the new variable can be whatever you want it to be, just like in summarize. So there are a lot of different helper functions. We didn't really need one for that example, but there are different things you can do with mutate. So for example, There's lag and lead. If you're working with longitudinal data, those can be very helpful. You can use like cumulative sums or cumulative products with these functions. And we can also use ranks. So we'll be using ranks here in a minute. We'll be using this min rank function. So there's a lot you can do with mutate. We're just gonna very briefly scratch the surface here this morning. So this min rank function is going to provide rankings for a set of values. So here we have 5 values. We have 50, 40, 60, 75, and then 50 again. And the min rank is going to assign a rank to each of those and give the lowest value the rank of 1. So 40 is the lowest, so it gets the rank of 1. 50 is the next lowest, and there's 2 of them, so they both get the rank of 2. No one gets a rank of 3 because these two were tied. The second and third place were tied. But then 60, the third value, gets the rank of 4, and 75, the fourth value in our set, gets the rank of 5. So it's telling you within this vector of values, what's the rank ordering among them. If you want to instead give the highest values the rank of 1, again, we can use that descending function that we saw with arrange. So that'll give us the ranks in descending order. So here 75 gets the rank of 1, and 40, our lowest value, gets the rank of 5. All right, so now we're going to play with min rank. So what I'd like you all to do is use mutate and the min rank function to rank each row in that baby names data from the largest proportion to the lowest proportion. So that means that the row with the highest proportion should have that rank of 1. All right, so we'll take a few minutes to work on this and then we'll talk about it. Okay, so how to tackle this one. So we are going to start with our baby names. And then I want to add a new variable. So that's going to be mutate. I'll call this the rank. And I want the rank of the proportions with the highest proportion ranked 1. So we'll use min rank to get the ranks. And because I want the highest proportion ranked 1, that's descending rank. So we'll use that descending function and then of the proportion variable. So if we run that, we now have for each name in our data set, the rank for that year. So we can see that Mary was the 14th most popular name in 1880. Anna was the 709th most popular name, and so on. And if we wanted to see which were the top, we could arrange that if we wanted to. So we could arrange by year and then by rank. That way we keep all the years together. Although I don't know what happened to number 2. That's a little concerning. We'll come back to that. All right. Okay, so now we want to figure out each name's median rank to figure out which name is the most popular, but instead of using the total number of names, we want to use a name's rank over year. So if a name is ranked highly every year, we want to call that popular. So to do this, we're going to compute each name's rank within each year and sex. We will then compute the median rank across years for each name and each sex. So I'll be using summarize. And then we will sort the results with the highest median rank to the lowest median rank. So we'll take a few minutes to work on this, and I will figure out what's happening with the other, why the rank 2 was missing. All right. So yes, Amber, you are correct. That is what happened with my turn 13. We did not group by year. And so that's why when I arranged by year, rank 2 was actually in 1881. So that's where that one went. So yes, that's exactly what happened. For 14, what we want to do is start with baby names. And then we want the rank for each year and sex. So we'll group by year and sex. And then we want to calculate the rank for each name by proportion. So we can use mutate and say the rank is equal to min rank in descending order of proportion. And so now we see for each row, we have that name's rank within each year and sex. And so now what we want to do is calculate the median rank for each name and sex. So now we will group by name and sex. And if you'll notice, our data frame is already grouped by year and sex. So when we use another group by, it's just going to overwrite the existing groups. So now if we run this, you can see that the groups have been overwritten. Our groups are now by name and sex instead of year and sex. And then we can summarize and say popularity is equal to the median of the rank variable. And it will think for a second. And now we have each name's popularity. And so remember, a rank of 1 meant the most popular. So the lower the score, the more popular the name. And so the last step would be to arrange by that popularity. And we can now see that Mary has the lowest median popularity score. So that would be the most popular name, followed by James, John, William, and Robert across all of the years in our data. Was everyone able to get these results? And does that make sense on how we are combining all of these different functions together to learn new things about our data? Thumbs up. Awesome. All right. So just to recap what we've done so far with dplyr, these have been all what are referred to as single table verbs. So you've just been working with that one baby names data set. So that'd be in like database language, that'd be called one table. So it's one single data set. And we can extract variables with select, extract cases with filter, arrange cases with arrange. We can compile summaries with summarize and create new variables with mutate. All right, and now, so we're gonna switch to joining data sets. So what happens when you have multiple different tables of data that you want to combine? We're coming up on a break, and this is a pretty good spot since we're kind of shifting gears a little bit. So let's go ahead and take a 15-minute break now. So we'll come back at 10:17 Central Time, and we will talk about how to join data sets together. I'll see you all in 15 minutes. All right, welcome back. So we're now going to shift into joining multiple data sets together. And again, there is a chapter in the R for Data Science book called Relational Data that also has a lot of details about this. So for this next section of slides, we're going to be using the NYC flights data. So this is a package called NYC Flights 13. And there are a few different data sets within this package. One of them is called flights. And that's this data that you see here. And so all of these are flights from the New York City area. So you can see the date of the flight. There's the year, month, and day, the departure time, the scheduled departure time, the delay. So like this one was scheduled to leave at 5:15, left at 5:17, so there's a 2-minute delay. Again, you'd see arrival time, scheduled arrival time, and a bunch of different other information about each flight. And within the package, there are additional data sets. So there's the flights that we were just looking at. There's also the airports. So those will give you airport codes for different airports. You have the tail numbers of the planes, different airline carrier information, and then also weather for when the flight was taking off. And these different data sets within the NYC flights package are related to each other, and you can match them based on the different information. So for example, this carrier variable is the same in the flights and the airlines. So if you wanted to match this carrier code to the name of the airline, that information is stored in the airlines database or airlines data frame and not the flights data frame. So if, for example, we look at all of the different carrier codes in the flights data, distinct is another function from dplyr that we're not going to talk about a whole lot, but that just gives you all of the distinct values. So if you say distinct for our flights and we want the carrier codes, it'll give you all of the distinct carrier codes within the flights data. So there were 16 codes. It's not, at least to me, always evident what each of these stand for, but in the airlines data, you can see that it has the code along with the name. So B6, for example, is JetBlue Airways. So there are different types of joins and ways that we can join these data frames together. There are mutating joins, which use the information from one data set to add variables to the other, just like mutate adds a variable to your data set. And then there are filtering joins, and these use information from one data set to filter another data set, just like filter does for a single verb or a single table. So to illustrate how this works, I have some toy data for us to look at based on MCU movies. So if you like Marvel movies, you're in luck. If not, bear with me here. So we have 3 different data sets. We have a heroes data set that has the hero name as well as their identity in the real world. We have a homes data set, which lists the place where each hero lives. And we have an enemies data set, which lists the villain for each hero that we have. So the first join we're going to talk about is left join. And so what left join does is it matches, it takes columns from the right data frame and adds them to the left data frame. So here, because we specified left join heroes homes, it's going to take the heroes data set that we have here and then add variables from the homes data set to it. And we tell it we want to join by hero because those are the two columns that are the same across the two data frames. And so when we do this, we get our original heroes data frame with the additional home column added. So Spider-Man, we know his home is in Queens, Black Panther is in Wakanda, and then Iron Man has a missing value for home because Iron Man does not appear in the homes data set. And similarly, Thor does not appear in our final answer because Thor was not in our original heroes data frame. So it just takes our heroes data and then joins what information it can from the homes data. Is that making sense how the left join works? All right, I'm gonna assume yes, but tell me if I need to slow down. All right, so the right join is just exactly the opposite. So it's going to keep the right data frame as is, and then add the information that it can from the left data frame. So here we have Thor, Spider-Man, and Black Panther and their homes from this original data frame here, and then we add their identities. So again, Spider-Man we know is Peter Parker, Black Panther is T'Challa, Thor does not appear in our original heroes data frame, so Thor has a missing value here. And then again, Iron Man and Tony Stark do not appear in our final answer because they were not present in our homes data. So that is left join and right join. And then the combination of that is the full join. So that says take all the information from both data frames and just give me as much back as you can. So here we get all of the heroes from both data frames. We're again joining by hero. And we see that Thor doesn't get an identity because he doesn't have one over here. And Iron Man does not get a home because Iron Man does not have one. But all of the information from both data frames is present in this final answer. So left join keeps only what's in the left and adds what it can. Right join keeps the right and adds what it can from the left. And the full join gives you everything together. The last mutating join that we'll talk about is inner join. And that's kind of the opposite of full join. It will only give you places where there is a match. So because Spider-Man and Black Panther are the only heroes that appear in both data frames, we only get their rows back. So our final answer only has Spider-Man and Black Panther, but it has the columns from both of the data frames that were used to join together. All right, so that was a lot of information. We're going to play with the joins now, so hopefully this will make a little bit more sense once you're able to get your hands on it. So what I would like you to do is to complete the code here. So I've blanked out the answers that you will fill in. What we want to find out is which airlines had the largest arrival delays. So you'll start with the flights. This drop NA is just going to drop any rows where the arrival delay is missing. Normally we might want to do something different with our missing data, but for our purposes today, we're just gonna listwise delete those rows for ease of use. And then here, I want you to join the airlines data to the flights data. Then you'll do a group by and compute the average arrival delay and then arrange that in descending order. So we'll take a few minutes to work on this and then look at how we can solve it. All right. So, all right, so if we look at our flights data, we have a bunch of different variables here. And the first thing that we need to do is join the airlines data to the flights. So we want to keep the flights and just add what we can from the airlines data. So that's going to be a left join. And so we want to left join the airlines. And in flights, we have a variable called carrier that we looked at earlier here. And in the airlines data, we also have a carrier variable. So we want to join airlines by carrier. And so once we do that, we now have the airline name has been added to our data frame now. And what we want to do is calculate the largest arrival delays by airline. So now we will group by this airline name that we've just added. So group by name. And then to compute the average delay, we can then summarize with the delay is going to be equal to the mean of the arrival delay, which is this R delay field. Right, and then to see the largest delays, we can arrange in descending order by that delay variable that we just created. So if we look at that, we can see that on average, Frontier Airlines had the largest delays, followed by AirTran and then ExpressJet. Does that make sense to everyone, how we join that information and then use it to calculate our summaries?
Quick question, for the left join.
Mm-hmm.
You didn't need to put flights after airlines?
We did not. So if you think about how the pipe works, it's sending, like the output of this is going to be the first argument here. So it's kind of like invisible. Like if you
Gotcha.
imagine like flights is going where this period is, like we're taking this and we're saying left join this and airlines. So just like when we do summarize, we don't have to say like we're summarizing the flights data. Like it just knows that we're summarizing whatever is getting piped in here. It knows that we're going to left join whatever is getting piped into left join. Does that make sense?
Yeah. In my code, I had done like right join, and then did airline comma flights. But yeah, right. If we're piping, shouldn't need to do that.
Yep.
Okay, thank you.
Yeah. All right. Okay. So that was our answer. All right, so what happens if we have non-matching names? So in that last exercise, the variable was called carrier in both the flights and the airlines data, but that won't always be the case. So for example, here we want to join the heroes and the enemies, but there is no variable that's the same. So heroes has hero and it has identity, and enemies has avenger and villain. And we know that the hero and the avenger are the same thing. They're just called different things. So we say we want to join heroes and enemies, and hero is going to be avenger. So it will match, assuming that these are the keys that they should be matching on, even though they don't have the same name. And so when it does, we get the left join as we would expect. So we get everything from heroes, and then it joins what it can from enemies. So Iron Man doesn't get a villain because there's no villain for Iron Man here. And then Thor does not appear because Thor is not in our heroes data. All right, so that was mutating joins, adding variables to another data set. So now we're going to talk about filtering joins that are used to extract cases. So the first one we're going to talk about is semi-join. So semi-join is going to return only the rows that exist in the second data frame. So a semi-join will take your first data frame, which in this case is heroes. It will return only the heroes data, but filtered to only cases that also appear in homes. So you start with your heroes data, and we're joining by hero. So we say, okay, which heroes also appear in homes? We're going to return only those rows. So because Spider-Man and Black Panther are the only two heroes that appear in homes, we get only those two rows back. But again, we only keep the columns in our original data frame. The opposite of that is anti-join. So anti-join is only going to return rows that do not exist in our second data frame. So here, again, joining heroes and homes, because Iron Man is the only row that does not exist in the homes, that is the only one that comes back. So question in the chat, how is semi-join different from inner join? Good question. So let's go back to inner join really quick. Inner join. So inner join is very similar. It's also only returning the rows that exist in that first data. So it's returning rows where there's a match, but it will also add the extra column from the homes data. So you get the same two rows that match, but you get columns from both of the data frames, whereas the semi-join is only going to return the columns from your original data frame. Yep. So these filtering joins, semi-join and anti-join, you'll only get your original columns back, and it will only do the filtering pieces. So yeah, semi-join will return the rows that match, and then anti-join will return the rows that do not match. So Iron Man doesn't have a match in homes, so that's the only row we get back with anti-join. All right. All right, so now we'll play with these filtering joins. So we want to know how many airports in the data were serviced by flights that originated in New York. And so what we want to do is take our flights data. Those are all of the flights that originated in New York in 2013. And then we'll take our airports data, which is another data set in that package. And we'll filter that airports data to only places that have a destination in the flights data. So we'll take a few minutes to work on this one, and then we'll come back and see what that one looks like. All right. So we have two data sets that we're wanting to join here. The first is airports. So this has all these different airports and their location. And for us, what's going to be important is this FAA code. And then we have our flights data, which includes a variable called destination. And so if we look at the distinct values of the destination and the flights data, we see that these are FAA codes. And so we want to know how many airports in this airport's data were serviced by flights from New York. So the way we do that is we'll start with the airport's data. And we want to semi-join. So we just want to keep what's in the airport's data, but we want to include only the rows that also have a destination in the flights data. So we'll semi-join to flights. And they are not named the same. So in the airport's data, it is called FAA. And that is equal to the dest variable in the flights data. So we say FAA equals destination. And then finally, we'll take the distinct rows to only see the airports. We only need one record for each airport. And so we get a data frame back that has 101 rows. So we know there were 101 airports that were serviced by flights from New York in 2013. Does that make sense how all that works? Does anyone have any questions about these filtering joins? Awesome. All right. So that is a high-level overview of joins with dplyr. In your cheat sheet, there is a whole section on combining tables, which also describes all the joins we talked about, along with some extra functions that you might find useful. But hopefully this is a good overview going forward. All right, so that is the end of our data transformation with dplyr section. Does anyone have any last minute questions or thoughts before we move on to our next topic? All right, so let me pull up the next slide deck. Okay. All right. So we are now going to talk about different types of data in R. So we've seen this just a little bit, but we're going to get a little more detailed about how R is actually storing and managing data. So we'll start with a little bit of a quiz. What types of data do you see in this data set? So I see a few. It looks like we have a date. So we have some dates here. We have what appears to be some character strings, name of airlines. We have a duration. So I'm guessing this is like the length of the flight. We have a number, which is the distance. And then we have some more character variables. You have the day of the week, and then we have some true false. So there's a few different types of data, and R helpfully kind of outlines what these are and how they're storing them. So R is storing this as a date time variable. We see a character string, a duration, a double, DBL is for double, which just means like a decimal based number. We have an ordinal, which is a factor that has an order to it, and then a logical variable, which is either true or false. So this is going to be a few different things. Mainly it's going to be around this like program sort of area of data science where we're not really changing the data. It's more just helping R process it better. However, that is going to involve a little bit of transformation. So if we have a data that comes in as a string variable that we want to convert to a date time, we'll look at how to do that as well. So we're going to talk about a few different data types this morning, but we're going to start with logicals. And so logicals are R's data type for Boolean values. And so Boolean is computer programming speak for true and false values. So there's this function in R called type of, which will tell you what type of data a value is. So if you do type of true, type of false, type of a vector of true and false values, R will tell you that those are logical. And so continuing with our flights data, we can make a logical variable. So if we take our flights, we can make a new variable called delay or delayed, and that will be if the arrival delay is greater than 0. So if the arrival delay is greater than 0, that will return a true, and if not, it will return a false. So if we do that and then select just the delay, the arrival delay, and that new delayed variable, we can see that cases where the delay is greater than 0, we get a true, and if it's less than 0, we get a false. And we can see again that that is a logical, so we get the LGL. And so from this, we might ask if we can compute a proportion of flights that arrived late from these true and false values. So the most useful skills with logicals are math with logicals. So when you do math with true false values in R, true gets a value of 1 and false becomes 0, which means that if you sum a vector of true and false values, the answer you're going to get is the number of trues. So here we have true, false, true, true. And if we take the sum of that, we get 3 because there are 3 true values. And similarly, that means that the mean of a logical vector is going to be the proportion of trues. So here we have a vector that is 1, 2, 3, 4. We say, are these values less than 4? That is going to be true for 3 of them. So 1, 2, and 3 are all less than 4. And so the average there is 0.75. So 75% of these cases are true. All right. So go ahead in your project and open up the exercises for data types. Should be 04 data types in your exercise folder. Run that setup chunk that will load your packages, and then use the flights data to create a new variable called delayed that indicates the flight was delayed or not. We just did that in the slides. Then remove all the rows that contain a missing value in that delayed variable and create a summary table that shows how many flights were delayed and what proportion of flights were delayed. So you'll need to use the summarize function here as well. So we'll take a few minutes and then come back together. All right. So let me first pull up the exercises. So we'll go to data types, run our setup chunk. All right, so now we want to create that new variable. So we'll start with flights, create a new variable called delayed. There's going to be, is the arrival delay greater than 0? Next thing we want to do is remove any rows that contain NA in the delayed field. So there are a couple ways to do this. You can drop NA for delayed. That's one way you could do this. You could also use filter like we learned yesterday and filter to where it's not NA for delayed. Both of those will do the exact same thing for you. And then we want to create a summary. So we want to know the total number of delayed flights. So that's going to be the sum of that delayed variable and the proportion of delayed flights, which is going to be the mean of the delayed variable. So we can see that there were 133,000-ish flights that were delayed coming out of New York. And that was just under 41% of all flights. Okay. So that's logicals. We're now going to switch to strings, also called character strings. And this is going to be anything that is surrounded by quotes or single quotes. So you can see like all of these are string variables. And so even if you put a number in quotes, R is going to think it's a string. And another thing to be careful about is that R is not very smart about closing strings. So if I'm in my console here and I start to like put my name in quotes, that works great. But if I forget the ending quote and I press enter, like R just is going to think that it keeps going. So if you ever find yourself stuck here and keep getting these plus signs, make sure your quote is closed. And then that will end it for you. So here it has my name plus all those times I pressed enter trying to get out. All right, so we're going to return to the baby names data in order to play with character strings a little bit. And so to start, we'll think about are boys or girls' names more likely to end in a vowel? This is kind of going to be our question that we're going to try and answer with these character strings as we go forward. So how can we go about calculating the proportion of boys and girls' names that end in a vowel? It seems like to me what we will need to do is first isolate the last letter of each name, determine if that's a vowel or not, and then calculate the proportion of vowels. Those are the steps that we're going to try and follow. So there are a few useful skills that you can do with strings in R. We're only going to focus on one of those today, which is how to extract or replace different substrings. And then the other two that we're not going to talk too much about are finding matches for patterns and regular expressions. But you can find plenty of resources for that. One place is the strings chapter of R for data science, which uses the string R package, which we will also be using today. But that chapter has a lot of details about the other skills that we will not be talking about. All right, so the first function we're going to talk about is str sub, so string sub. And this is going to extract or replace portions of a string with whatever we tell it to do. So the way that this works is you use str sub with your string and you tell it where you want it to start and where you want it to end. And so by default, the start is the first character. And by default, the end is the last character. So -1 means the last character. So again, the string we're going to manipulate, the position of the first character and the position of the last character string. All right, so pop quiz time. What will this return? So if we say Mephisto, start is 1 and end is 2. Yes, that's correct. So we start at the first position, end at the second position, which means we get those first 2 letters, which are me. Okay, this is the same slide again. Sorry about that. What will this one return if we only give it a starting position of 2? So remember yes, correct. By default, the ending position is the last character. So if we start at position 2 and go to the end, we get just the Mephisto. All right, another one. What is this one going to give us? Correct, yep. So we start at the third to last position and go to the end, so we get just stow. All right, so now what do we think this one is going to do? We're saving a string Mephisto called M, and we're going to take that string, use str sub on it, and then send in Agatha. Will it replace stow with Agatha? Yes, that is exactly what's going to happen. So it will take those last 3 characters to the end and get rid of them and replace them with whatever we've put inside these quotes. So this is the answer that we would get out of there. All right, so now we're going to play with some strings a little bit. So I've provided some template code in the file. And so what I want you all to do is to complete the blanks in the code to do these steps. So we want to isolate the last letter of every name. And you'll do that with the str sub function. You'll then create a variable that indicates whether the last letter is one of A, E, I, O, U, or Y. And then calculate the proportion of children whose name ends in a vowel by year and by sex. And then finally, we're going to put that into ggplot to make a line plot. So we'll take a few minutes and then we'll look at what this plot looks like. Okay. All right, so we're going to start with our baby names data. And we want to add some new columns. So that's going to be mutate again. So to get the last character or the last letter of the name, we're going to use our str sub. And we want to use the name variable. And we want to start at the last character. And we also want to end at the last character. Oops, end equals -1. So this will give us just the last letter. And then to determine if it's a vowel, we want to know is the last in A, E, I, O, U, or Y. All right. And so if we run just this section here, we now have a data frame that has the last letter of each name, and it includes an indicator of whether that last letter is a vowel or not. So then we can group by year and sex, and we'll use summary or summarize. And to calculate the proportion that are vowels, we're going to do a weighted mean of this vowel variable. So weighted mean is a function that's already built into R. And so we want to use that because like this Mary, there were 7,000 children who had the name of Mary, and only 2,000 children who had the name of Elizabeth. So we don't want to give like both of these rows the same weight in our mean because there were many more children with the name of Mary. So the weighted mean, we can tell it to weight by this n column, and that'll give us a better overall proportion. So if we do that, we can then see that for each year and each sex, we get the proportion of names that are ending in a vowel. So finally, we can create our ggplot. So on the x-axis, we want the year, and on the y-axis, we want the proportion that were vowels. And we'll do a geom line, and we'll color by sex. Okay. So if we run that, we can then see the proportion of names that end in a vowel for both girls and boys. And overall, we see that female names are much more likely to end in a vowel than male names are. So is everyone able to get this graph? And does it make sense how we got there? Awesome. All right. All right, so now we're going to talk about factor variables. So factors are R's representation of categorical data. So they consist of a set of values and an ordered set of valid levels. So for example, if we're looking at eye colors, we might call that a factor variable. So we can say that we have data on eye colors for 3 people, and their eyes are blue, green, and green for the 3 people. We can say, but there are other levels that could be for eye color. So in addition to blue and green, we might also have brown eyes and hazel eyes. And so then when we look at what is in this eyes object, we see that it has 3 values, blue, green, and green, but there are 4 levels that these values could possibly take. Internally within R, factors are stored as integers, which is just non-decimal numbers. So if you look at i's and use unclass that says don't call them a factor, just question in the chat, wouldn't these also be strings since they are characters within quotes? Kind of, yes. So they will look like strings when you are typing them in R, but because we're wrapping it in this factor, we're basically telling R to do extra things with it. So it's like it's a special character almost. So like a character string can take on any value, whereas with a factor, we're saying it can only take on like these specific values. So it's a little more constrained than just a character string. All right, and so because we had blue, green, green, we would get values of 1, 3, 3 because blue is the first level and green is the third level. All right, so to work with factors in R, we're going to use the for-cats package, which stands for for categorical. Also, there's just like a lot of cats in R, as you might learn as we go through this. So there is a chapter in the R for Data Science book called Factors, which talks about this a lot. And again, as we have kind of already been doing through this section of slides, we're going to talk about factors at a high level, but there is much more detail that we could go into. All right, so our motivating question for this factors section is going to be, do married people watch more or less TV than single people do? So this data is going to come from GSS CAT. GSS is the General Social Survey. It's a long-running US survey conducted by people at the University of Chicago. And so you can see there's a year variable. There is a factor of marital status. So you can see there's divorced, married, never married, widowed. The survey taker's age, race, income, political party affiliation, religious affiliation. And then also there are TV hours. So how many hours a day did this person watch TV? All right, so before we get to married people, we will start with which religions watch the least TV. And the way we can do this is we start with our data. We drop rows where there are missing TV hours, group by religious affiliation, calculate the average number of TV hours for everyone who reported a given religion, and then we create our ggplot. And when we do that, which of these is easiest to understand or even just like pleasing to look at? For me, it is very much the plot on the right. It's much easier for me to see that these are in like increasing order. And then I can like more easily see like what's going on. Whereas the one on the left is just kind of scattered all over the place, and it's hard for me to gain any insights when the data is arranged like that. So a pop quiz for you. Does anyone know why the y-axis is in this order by default? So the answer, excuse me, is that those are the default levels of the factor. So if we look at in our RStudio, this GSS cat data, if we look, you can access the levels of a factor using the levels function. So if we look at the levels of GSS cat relig, we see that they are in this order, and that's the order that it's automatically going to show up on the plot. All right. So again, if you compare this ordering to the plot, you'll see that it goes from the first to the last. So the most useful skills with factors in R that we're going to talk about are how to reorder the levels, how to recode the levels, and finally how to collapse levels together. So we're first going to talk about reordering levels. This is done with the FCT reorder, FCT for factor. So we're going to reorder a factor. And this will reorder the levels based on the result of some function applied to each group of cases. So we're going to give it a factor variable f that's going to be recoded. We're going to give it a variable to reorder by in conjunction with the function. That function can be the median, the max, whatever summary function we want to use. And then there's a descending option for whether we want to put the values in descending order or ascending order. And so the way you do this in ggplot is we can say that we want to calculate our same summary we did before. So calculate the average number of TV hours by religious group. But then in our ggplot, we can say on our y-axis, we want to reorder the relig factor variable by TV hours and the mean of TV hours. So then when we do that, we get the highest TV hours at the top and the lowest TV hours at the bottom. So we'll automatically reorder your factor levels by the average of whatever variable you want, or the median of whatever variable you want. So you can do any summary function here, and then whichever variable you want to order by. All right, so let's try this out. You all are going to complete the following code again to calculate the average number of TV hours by marital status, and then create a sensible plot of average TV consumption by marital status. You can play with the factor ordering to find one that you think makes the most sense. All right. So to do this, we first start with our data, and then we want to group by marital status. Marital, and then we can summarize and say that the average number of TV hours is going to be the mean of the TV hours variable. So that gives us the average for each marital status. And finally, we can make our plot. So we say we want TV hours on the x-axis, and on the y-axis, we want marital status. That gives us a not great bar graph. So we can reorder that. We say fact reorder. Make sure I close my parentheses. And we want to reorder that by TV hours, and we'll do the mean. And so now we get a nice chart showing the average number of TV hours for each marital status from people who responded in this survey. All right. So there are a few other ways that we can rearrange factors. We can do fact in freq, that is short for in order of frequency. So if we just wanted to know how many people are there with each marital status, we could do that with geom bar and then use FCT and freq, and that will put it in the order of frequency. So we get the most frequent on the left all the way to the least frequent. We can also do factor reverse, so we can reverse the order. So here we again use and freq to do order of frequency, but then we reverse that. So this would be the normal order, but we can reverse to go from lowest to highest as well. So those, the last two, the frequency and the reverse, are most useful if you're just counting. If you want to do summaries, then factory order is going to be better for you there. All right, so next thing we're going to talk about is recoding levels. So for this one, we'll be looking at, do people who identify as liberal or people who identify as conservative watch more television? So to do this, we're going to compute the average TV consumption by party identification and then plot the results. All right, so this one's going to look pretty similar to how we've been doing this in the previous couple examples. So again, we'll start with our GSS cat data. And we're going to drop any places where the TV hours is missing. We will group by party ID this time. And then we'll do that same summarize of TV hours is the mean of TV hours. And we'll send that to ggplot. And say on the x-axis, we want TV hours. On the y-axis, we will reorder the party ID value by TV hours. We'll add a geom call. And finally, I'll change the label of the y-axis to be party ID. And so that gives us this graph, which shows the number of hours or average hours of TV by political party identification in our survey data. So the question then is how we can improve the labels that are in this plot. So some of these seem pretty similar. Some of them are maybe not very clear what they mean. And so factor recode is what's going to help us change the levels of a factor in order to make more sense. So the way this works is we send it a factor variable, and then we give it new level and old level pairs. So we say, here's what we want the new level to say, and here's which old level that maps to. Why can we leave the geom call blank? So good question. So geom call and geom bar are very similar. The difference is that for geom call, you are specifying a Y aesthetic. So for example, we have set up here like this is the Y value, or in this case, it would be the X value since that's the direction the bars are going. So we're giving it, like we're telling it how long the column is or how long the bar is. For geom bar, that is more of a, that's for a count. It's like if we wanted to count the number of people that identify with each party affiliation, we could say a ggplot for GSS cat. Let's say on the x-axis, we just want that party ID. If we say geom bar, that will give us a bar graph that is the count of the number of people in each party. So for geom bar, the Y aesthetic is unspecified. For geom call, the Y aesthetic is specified. And it'll give you warnings if you do the wrong one. So like if I try and specify geom bar when I've already set a Y aesthetic, I will get an error that says like I can't have a Y aesthetic for this. So if you try and do the wrong one, you'll get an error to let you know about it. And so for like why this is blank, it's blank because we don't actually need to specify anything new. Like we've already told it the aesthetics that it needs in our global mapping up here. So yesterday we talked about a global specification versus a local specification. So we've told it which aesthetics to use. So it doesn't need to know anything else other than we want columns. So that's why we can leave it blank. Does that answer your question? Awesome. All right. So for recoding factors, the way that this works is we say we're gonna update this party ID variable, and we're going to recode the factors. So we're recoding party ID, and on the left side are the new labels, and the right side are the old labels. So these ones over here are the labels that currently exist in our data. And we're saying, okay, if it's strong Republican, we're going to rename that as Republican, strong. Not strong Republican is Republican, weak, and so on. So this is maybe a better way to look at the data, since you'll have all of these that are more conservative leaning will start with Republican, all the ones that are more liberal leaning will start with Democrat, and so it's easier to group those levels together. And so if we do that, then our plot is kind of easier to see what's going on. It's easier to pull out. These are the more liberal ones. These are the more conservative ones. All right. And so again, just that plot again. But we can improve this even more. So as we just mentioned, like these three Republican labeled ones are more conservative. Then you have these three ones, which are more liberal. And it might be helpful to kind of combine these into a single group. And so that brings us to our last topic for factors. So we'll get through this one and then break for lunch. We're going to talk about collapsing factors. And so to do this, we'll use a function called FCT collapse. So all of these factor-based functions start with FCT. So factor collapse is going to change multiple levels into a single level. So again, we send it a factor, and then we give it the labels to be collapsed. And so the way this works is we say we're making a new party ID, and we're going to use fact collapse to do that. And so we're going to start with the party ID variable, and we're going to say anything that is in these three categories, we're going to call conservative, and anything that's in these three categories, we're going to call liberal. And now when we make this graph, we see we have, this is the number of people in each of these categories now. So we have a lot of people in the liberal category, a lot of people in the conservative category, and then fewer people in independent, and then even fewer in these other or no answer provided categories. And so we also might want to group those together, like group together the ones that are extremely small into a single other category. And we can do that with factor lump. So we can kind of lump these other ones together. And so it's going to collapse levels with the fewest values into a single level. And the default behavior is to collapse as many levels together as possible so that the new lumped level is still the smallest in the data. So we give it the factor that needs to be lumped together, the number of levels that should be lumped. So it's the n smallest levels. And then the name of the new level. So how this would work with our data. Again, we start by defining this new party factor variable that is conservative if you're in any of these three categories, liberal if you identified any of these categories. And then finally, we take this new party and we're going to lump it together. And we're going to take the lowest three levels and call them collectively other. And so when we do that, we now have just liberal, independent, conservative, and other are the four groups left, and the average TV hours for each of those groups. Does that make sense how we can kind of take our factor levels and reorder them, regroup them, rename them in order to get levels that make more sense for the story that we're trying to tell. Awesome, great. All right, so we will go ahead and break here. When we get back, we will talk about dates and times in R. So we will be back at 1:30 p.m. Central Time. And I hope you all have a great lunch. Just like yesterday, I will leave the Zoom open throughout lunch. So feel free to stay logged in if you want, or leave and log back in when you get back. I'll see you all at 1:30. All right, welcome back, everyone. I hope you all had a good lunch. Maybe relax your brain for a little bit. So before we left for lunch, we were just getting ready to talk about dates and times in R. So we will pick up there with a little thought exercise. So out of context, you might think that like dates and times are like fairly easy to handle. But in reality, there are catches that make things difficult. So for example, not every year is going to have 365 days. Does every day have 24 hours? I mean, not exactly. Does every minute have 60 seconds? Also, usually, most of the time, but not always. And then what does a month measure? So for example, like what's 1 month after January 31st? There is no February 31st to go to. So what is a month if you say this is 1 month from now? So these are all things that we have to figure out how to handle in R if we're working with data that has dates associated with it. So the skills we're going to talk about today are creating dates and times. So parsing character strings or other things that have date information but are not encoded as dates. How can we make R recognize those as dates? And then accessing and changing parts of a date. There are a couple other useful skills that we're not going to talk about today, and that's dealing with time zones and doing math with time instance and time spans. But I will give you some resources for those if you're interested. So to start, we're going to use the flights data again to think about dates and times, and we want to think about what the best time of day to fly is and what the best day of the week is to fly. So those are going to be our guiding questions as we talk about dates. So we're going to focus briefly on the relationship between the scheduled departure time and the average flight delay. So here we have the scheduled flight time and then the delay, which is not included here, but that's what we'll be looking at. So if we make a plot, we might just make a plot of departure time on the x-axis and the arrival delay on the y-axis, and add some points and a smooth curve to get an idea of what this distribution and what this relationship might look like. And when we do that, we get this sort of curve, which looks very much like a straight line, but it's really hard to tell what's going on here. So the question is like, what's happening here? And so for minutes, like minutes stop at 59 because there's only 59 minutes in an hour. So we get these gaps from 60 to 99 for every quote unquote hour, right? Because there's no like 568, like that's not a time that exists. So R is not recognizing this as a time. It thinks it's a number. And so it says, oh, it goes from 500 to a little over 2000. And there's just these like weird gaps where there's no data. So we need to let R know that this is a time so that we can get a more meaningful plot to understand our data. And for using dates and times, we're going to use the HMS package for hours, minutes, seconds. And again, there's a chapter in R for Data Science on dates and times that is linked to here. So in HMS, you have a date and a time. So here we're going to focus on the time element. And this is stored as the number of seconds since 0, 0, 0, 0, 0. So the number of seconds since the beginning of the day. So if we do, if we load the HMS library, we can then use the HMS function and say 34 seconds, 52 minutes, and 14 hours. And we get like this time that says it's 14:52:34, which is almost 3 p.m. if you're using the 12-hour time instead of 24-hour time. And if you unclass this, so you tell R, so don't think this is a time anymore, then it shows that it's right about 53,000 seconds from this like beginning time. So we want to control this in R. So we are going to look at what the best time of day to fly is. So what I would like you all to do is use the hour and minute variables in the flight's data to compute the time of day for each flight as an HMS. And then once you have done that, use a smooth line to plot the relationship between the time of day and the arrival delay. So we want to make something similar to the plot that I just showed you, but actually have a time on the x-axis instead of just the number. So we'll take a few minutes and then look at how we can do this. All right. So the way we can do this is we start with our flights data. We then use mutate to make a new variable, which I've called time. And we use the HMS function and we set hours to the hour variable in our flights data and the minutes to the minute variable in our flights data. So that's how we create our time variable. And then we send that to ggplot with the same sort of code we used before. So we put this time on the x-axis and then arrival delay on the y-axis. And then we add points and our smooth curve. And that gives us a plot that looks like this, which is better. We no longer have these weird gaps in our data. And it's more clearly a time that is along our x-axis here. We can also make an improved plot. So here we have the arrival delay going from -5 to 15. If we don't plot all the points, so we have some like very big outliers in here that is making this curve look basically straight. But if we don't plot the points and we only plot the curve, then we can see more of what's going on. And so you tend to have shorter delays or no delay if you're flying in the morning. If your departure time is in the afternoon or the evening, that's when you start to have higher delays on average. So if our question is when's the best time to fly, that would be the morning, as long as you're okay getting to the airport on time. All right, so for the dates part of dates and time, we use the lubridate package. And again, this is described in that dates and time chapter of R for Data Science. And lubridate has a whole family of like year, month, day functions that are used to parse dates out of character strings. Excuse me. So the way that you use these functions is you have a character string that is a date, and you tell it what format it's in. So here we have a year, a month, and a day. And so we use the YMD function for year, month, day. In this next example, it's month, day, year. So we use the MDY function to say, okay, parse a date that's in the month, day, year format. And both of these result in the same output from R. So this is how R is encoding it. You just have to specify the format that it comes in. And if you have a character string that is dates and times, so here we have a specific time on May 4th, then you can use the year, month, day underscore HMS. So it's the format of the date and then the format of the time. And it will give you a date time object that's parsed from your character string. And then we can access components of those dates. So if we say that Star Wars is May 4th, 2021 for Star Wars Day, then we can use the year function and it'll tell us what the year of this date is. The month will return the month of our date, the day will return the year of our date that we have, or the day will return the day of our year. So we can extract the components of a date object once it's been created. Similarly, we can set the components. So we have Star Wars with a date of May 4th, 2021. If we say the year of Star Wars and set it to 2002, then if we look at Star Wars, it now has a 2002 date instead of the 2021 date. So we can access as well as set the components of a date. So there are many different ways and components you might want to extract from a date. These are the most common. So there's the year, the month, and for the month, you can specify whether you want the label. So before, on the last slide, or 2 slides ago, we got 5 from the month. If we wanted the name of the month, then we could set label equal to true. in order to get the month name. And then abbreviation is whether you want the month abbreviated. So for example, Jan, Jan for January. So abbreviation true will give you the abbreviation, set it to false to get the full name. You can get the week, so that'd be the week of the year, the day of the month, the weekday, which again, you can either label and abbreviate or not, if you wanted like Monday, Tuesday. And then you can also get day of the quarter, day of the year, and then hour, minute, second. So you can extract all these different components from a date object once R knows that it's a date. So for example, if we look at the weekday of Star Wars, we get a 7. If we turn label equals to true, we get Saturday. And we see that this is a factor because it has levels. And it's an ordered factor. So it tells us Sunday is less than Monday, Tuesday, Wednesday, Thursday. So it gives us the order. Saturday is last, which is why we got a value of 7. And finally, we can set abbreviation to false to get the full weekday names instead of the abbreviated weekday names. All right, so now we're going to use that to complete, again, this template code. So what we want to do is extract the day of the week as the full name for each flight from the time hour field. We then want to calculate the average arrival delay by day of the week and plot the results as a column chart or bar chart with geom call. All right, so let's look at how we can do this one. So we want to extract the full weekday from the time hour field in our flights data. So we'll use the wday function to get the weekday from the time hour. And we want the full name, so we'll say label equals true and abbreviation is false. And then we want to calculate the average arrival delay by day of the week. So we need to group by that weekday variable that we just calculated. And then we can summarize and calculate the average delay as the mean of the arrival delay. And if we look at just this, we now have an average delay for each day of the week. And so we can make our ggplot and put weekday on the x-axis and the average delay on the y-axis. And if we use geom_call, then we get our bar chart. And so we can see that if you're looking for the best day of the week to fly, Saturday tends to have no delay out of New York City at least, whereas Thursday tends to have the largest delays. All right. And so that is everything for data types. So we talked about strings, factors, date times, and logicals. So this is a less data analysis sort of thing, but is I think one of the very overlooked parts of data science and analyzing data is really making sure that your data is in the right structure and the right format in order for your programs to analyze it correctly. So hopefully this is helpful. And if no one has any immediate questions about these, we'll go ahead and move into our next set of slides, which is going to be on importing data. All right. We're a little off center. Okay. So importing data, kind of like data types, is I think something that gets overlooked because in general, it is like incredibly boring, or it's just absolutely infuriating if it's not working correctly. However, it is like the foundation of any data analysis you will ever do, because if you can't get your data into your software program, you kind of can't ever analyze it. So it's something that we need to talk about to figure out how we can get data into R. So go ahead and open the new notebook. So that is exercises and then O5 import, and run the setup chunk and see what happens. All right, so how many of you got an error? Yes, so everyone should have gotten an error. So what happens when you run the setup chunk? I didn't get an error. I got a warning, but that's because this file path exists for me. Like this is a folder path that exists on my computer, but it does not exist on your computer. And so this is like a #1 problem in importing data, is that I put together like an R project. I put the data on my computer. I read it into R. I'm like setting my working directory to my data file. I send it to someone else, one of my collaborators. They try and run it and it breaks. They can't read the data in because this file path does not exist for them. So we're going to talk a lot about importing data today, but in this section, we're also going to talk about how to set up project directories in a way that they are easy to use for collaborators and also easy to use for yourself. So if you're switching computers or you get a new computer, how to prevent file paths from breaking all of your old projects. So again, yes, that's going to give you some errors. And so there are a couple things that are problematic in R scripts. And we're going to focus on this first one, which is if the first line of your R code is setting some working directory, then it's going to be problematic because your collaborators will not have that working directory. So the lesson of this is to be kind to your collaborators, including future you, who is always a collaborator, whether you want them to be or not. So there are workflows as part of like projects that will get shared. That includes like your editor that you're using, RStudio. Your collaborators may not use RStudio. They might use a different software program or a different interface to R. You don't have to use RStudio to use R. There's your home directory, which will not be the same for your collaborators. And there's R code that you ran 6 months ago that you may not remember why you ran it or what it's supposed to be doing. And then there are product objects. There's raw data files, and there's R code that someone else needs to be able to run in order to replicate your results. And the bottom line is that workflows should not be hardwired into the products. So someone should be able to access the raw data without having access to your home directory, right? They should be able to run the code without relying on options that you've set in a way that they cannot also set the same options. So we'll talk about how to do this with our projects. So you think about each analysis that you're doing as a separate project. And so each project is a folder on your computer with all of the relevant files for that project. You can move this folder to a different location on your computer. You can move it to an entirely different computer. You can send that folder to another person. Everything that you need for this analysis is in that one project directory. And R scripts can be written with the assumption of a clean session and a working directory that's equal to the project directory. That's going to mean that all of the files are in an expected location that everyone will be able to access. And the final piece of a project is that it creates everything that it needs. So if it needs an intermediate output file, the project is creating that. And it doesn't touch anything that it didn't create. So it's not setting options that are going to be specific to your computer that a collaborator can't replicate. And so this is just like agreeing that we're all going to drive on the left side of the road or the right side of the road. It's just conventions that constrain our behavior a little bit. in the name of everyone else getting along and being able to work together better. So the way that we're going to manage this is with the here package. Again, there's a chapter in R for Data Science about workflows with projects, but the here package is really going to make this problem of finding data files very easy for us. So here, there's a function called here in the here package, and it is going to find the project directory and build file paths for you. So if all of you in your console do library here, and then the here function, we should all get different results. It's like if I pull up mine, I do library here, and it's going to tell me that here starts at this directory where all my files are saved. If you do this, you should get a different thing. It'll tell you whatever the working directory of your project is that we've opened here. And so this is, even though we're calling the same function, right? We're just loading the package. And if we use the here function, it'll give me that same information. It tells me where the root of my project is. We can use the same function to get user-specific information about where our project is located. And we can use that to build file paths. So if I say here, and then we go into the materials folder, and then the data folder, and then we look at nimbus.csv, it'll build this file path with the assumption of this working directory. So I can use this code, you can use this code, and we'll get different file paths that still point to the same data file. And so here, how does it know where to start? So it looks for a file named .here, or it looks for a .r project file, which is what we have. If you look at the root of our project, there's this tidyds 2021.r project. So that's our project file. And because this is here, the here package knows that this is the root of our project. But if you don't have either of these, it'll also look for a Git directory if you're using GitHub, which is something that we're not going to talk about, but can be very useful for you. All right, and you can also use the dr here function, and that'll tell you where your project root is and also why. So that's the directory because it found an R project file. All right, so now that we have the here function and package, we can import data using the readr package. And readr can be used to import a ton of different data file types. So we'll highlight a few of those here. And then I'm also going to give you some resources to import other data file types that are not accessible with readr. So again, this is like the very first step of any data analysis is going to be importing your data so that you can even get to the rest of the steps in our pipeline here. So readr has a ton of functions based on the type of data that you are importing. So it can read CSV files, semicolon separated files, any sort of general delimiter. So if you have a tab separated file or space separated file, those have special cases down here, but you could have any sort of delimiter. They also have fixed width files. So these are the most common. But for us, we're going to focus on CSV because this is, at least in my experience, the most common way to get files out. So we're going to use the Nimbus data. And this is ozone data at different locations. So we have the date the measurement was taken, the latitude, the longitude, and then the ozone measurement. And this is a comma separated file. So you can see each element is separated by a comma. And because we have comma separated values, we can use the read CSV function, and all of the reader functions are going to share the same syntax. So it'll always be read whatever type of file you're importing, and then the path to the file. Dat is what we want to save that object as in our R environment. So we have to save it as something. And then the path to the file. But again, we don't want to just write the path, because the path that I would write is not the same path that one of you would write on your own computer, because we don't have the same directory structures. So we're going to build our paths with the here function. So we'll use here path to file is how we'll build those. So we're going to practice. You have the Nimbus data in your data folder under materials in your project. So I want you to find that CSV file in your project directory and then read it into R with the read CSV function and the here function to define that file path. All right, so we'll take a couple minutes to do that, and then we'll make sure that we're all on the same page for how to import data. All right. So the way that we can do this is we can I'll just call my data Nimbus. Then we want to read CSV, and we want to build the path. So we'll start with here, and then we want to go into the materials folder. So we'll do materials, and then into the data folder. So data, and then our file is called nimbus.csv. So if we run that, we get a list of column specifications. So it told us how it read the data in. It read in the date as a date time, the longitude and latitude as doubles, so those are just decimal numbers, and then ozone it read in as a character variable. And if we look in our environment, we can now see there's this Nimbus data object that's in our environment ready for us to use. And we can look at that by typing Nimbus into our console, and we can see those 4 fields again: the date, the latitude, longitude, and the ozone and it has the data types that were specified by the column specification here. So now we're going to talk about tibbles. And you might be wondering what a tibble is. So tibbles are a way to manage data in R. And even though you did not know it, you've been using them all day, yesterday, and today. But now we'll kind of like pull back the covers a little bit to look at what's been going on. So there are actually two different versions of this read CSV function. There's read.csv. That's in base R, so that comes with R. You don't need the tidyverse for read.csv. And then read_CSV is the tidyverse version. So if you use read.csv, your data in R is what's called a data frame. And so if you look at your data as a data frame, you get something that looks like this. You get all of your variables and all of your rows, and it'll just show you as much as it possibly can. Whereas if you use read_CSV, you get this different version that we're more used to looking at, where it actually has the column names. It gives you some more information about what type of data is in each column. And it's only showing you the first 10 rows. So it's a little more truncated, but a little bit easier to look at. And so if you look at a data frame, it is going to just spit out as much information as it possibly can. And then what ends up happening is that you end up only actually seeing like the bottom right corner of your data frame, which is not super helpful, like if you're trying to understand what's going on. Whereas a tibble is going to show you like the top left corner. So it'll show you as many columns as it can fit in your console, and then it tells you what the rest are, and it'll only show you the first few rows of that data. So it's a little easier to manage and see what's going on, I think anyway. So in the data import cheat sheet, or no, this is in the data tidying cheat sheet. We're going to talk about the tidyr package this afternoon. But there is a section on tibbles and why they are important. We don't need to understand much more about them other than it gives us a nice tidy way to look at our data. And that's why we have this extra information included. So if you are looking up help on R or looking at questions on the internet that people give it answers to, and you don't see like this type of information, just know that it's because they're using data frames instead of tibbles. And by default, the readr package will give you tibbles. All right, so now we're going to talk about parsing. So how does readr decide like what type of variable it's going to assign each column? So when we look at the Nimbus data, like what type of data is ozone? And we looked at this a little bit earlier. So the ozone is coming in as a character vector. But when we look at the unique values of ozone, so if we look at the unique values of ozone, what we see is like these are numbers, like they appear to be numbers to me. The discrepancy is that we have like one period. And because there is a period, R thinks that, well, this must be a character string because a period is not a number. But these are all actually missing values. So the data was coded in a way such that if there was no ozone measurement at a given a latitude and longitude on a date, they just coded that data as a period. So we need a way to tell R, hey, missing data in this data set are periods. And we can do that in the read CSV function. So there's an argument called NA, and we can say, hey, anywhere you see just a period, make that a missing value in R. All right, so why don't we go ahead and try that? We want to read in the Nimbus data again, but this time we want to set missing values or set periods to be missing values. And I see there's a question in the chat that I missed. If you're getting a message that says could not find function here, just make sure that you have the here package installed. So I'll restart my R session. So if you do install .packages here, then it will install, and then you should be able to do library here, and then you'll have the here function. So yeah, just make sure that you have the package installed. All right. So in our original solution, we had just done read CSV and then the path to our data, and it read it in as a character. It was a character in our tibble. And now if we add NA equals period, now we can see the ozone is getting read in as a number. Call double is again a decimal number. And so we see that it's a number in our data now too. So it's recognizing that that period is a missing value. You can also manually specify the column types. So if R is just not reading it in the way that it should or the way you want it to, you can override what it's doing. And so you can specify that. You can say call types equals calls, and then you do the variable from your data and what type of column it should be. So here we say bar1 in our data should be a number column. And there are many different specifications you can have. So you can force it to be a character column, a date column, a date time, a number. The default is this call guess. So this is what readr is doing by default. It is guessing based on what it's seen in the first few lines of the data file. It's going to guess what type of data it is. Then you can also specify logicals, numbers, time. So there are a lot of different options. And again, that's going to be similar to our data types that we were looking at earlier. So if you wanted a factor, you could force it to read in as a factor variable. All right, so now we're going to read in Nimbus one more time, but this time we also want to force it to read in ozone as integer values. So none of our values of ozone actually have decimal numbers. They're all round integers, so we can force R to read that in as an integer value. So we'll take a couple minutes to add that, and then we'll come back and look at some last little things for data importing. All right. So again, the way we do this, we have our same code as before. We write our file path using the here function. We specify NA values as periods, and then we add this new line of code. So we say call types, and then calls are ozone is going to be a column integer. Because we don't specify the other columns, it's going to continue to guess for those. But now we see that longitude and latitude are doubles or decimal point numbers, and ozone is an integer. So these are all round numbers. As a bonus, we can actually map the ozone around the world with this longitude and latitude. We're not going to talk about like how to make this map necessarily, but if you're interested, the code is here, and that's what it looks like. So you can make, again, just an example in ggplot of all the different types of plots that you can make using the same sort of ggplot code, mapping it with aesthetics, the same sort of process, but again, a more specialized geographic representation of that. All right, so let's briefly talk about other data files that are not accessible in the readr package and how you would use those. If you have Excel files, so these are super common XLS or XLSX files, the readxl package is going to be very good for you. These packages all have very similar, if not identical, syntax to the readr package. So for example, there's a read_xlsx function, and it works just like read CSV. But that's in the readxl package. If you have data files from other stat software, so if you have a collaborator that works in SPSS or Stata or SAS, and they send you a SAS data file, you can use Haven in order to read those data files into R. You can also use Haven to write data files for those different software programs. So if you have that Nimbus data loaded into R, you could write that to a Stata file if you wanted to or needed to. You can also use the Google Sheets 4 package and Google Drive package in order to access files that are on Google Drive. And then finally, there's a package called, I guess not finally, I guess I have a couple more slides that I forgot I had. There's a package called Feather that is really good for efficient data sharing between R and Python. So if you have data, really large data files that are going back and forth between R and Python, Feather will be good. You can also scrape data from the web. So if you've heard of web scraping or familiar with that, the rvest package, it's supposed to be kind of like harvest, but rvest is really useful for scraping data from the web. So that's where I would go if you're looking for that type of data import. There are also a number of other packages that can be used that don't have nice logos for me to put up yet, so they all get on one slide. If you have JSON data, you can use JSON Lite, similar for XML data. The tidyr package, HTTR, is for web APIs. And then the DBI package is very good if you have like databases, like a SQL database that you're accessing. The DBI package is very good for that sort of information. So that is a very high level overview for importing data. As I said, there's not a ton to talk about here because it's either really boring or incredibly frustrating because it doesn't work. But hopefully you don't have too many problems importing data. And it usually is pretty smooth, especially with the readr package. They make it very easy. Does anyone have any questions? So I see one in the chat, a message saying you need to install R tools to install the here package. You should not need to do that, I don't think, unless it's trying to install a source version. If you have time, right after we're done today, I can help you troubleshoot that. Or if you want to sign up for office hours, that'll take a little bit of finagling on your machine that will be hard for me to do without seeing it. But if you install packages, like install packages here, and it asks if you want to install the source version, you can say no, and it'll install the binary version. And for that, you should not need R tools installed to get the binary versions from CRAN.
Yeah, I got the same warning message, and then the package here successfully unpacked after I got the warning message, and I didn't do anything.
That's really interesting. I didn't, so under the hood for how CRAN works, like you submit a package there and it's like a source version, and eventually CRAN will build a binary that's easy to install. So my guess as to what's happening is that the people who write the here package just submitted a new version to CRAN. And so only the source version is up right now. The binary hasn't been built yet. And so if you're on a Windows machine and you try and install a source package, it will tell you that you need R tools. Yeah. Yeah, and this was my mistake in the pre-work page where I listed all the packages that you all should install. I did not list the here package, which is why you're all getting errors that you need to install here. It's because I forgot to put it in that list of packages that needed to be installed. Yeah. All right, so we will, looks like we are at our time for a break. So we will take 15 minutes. So we'll come back at 2:50 Central Time. And then we will start talking about how to tidy data. So 2:50 Central Time. All right, go ahead and give me a thumbs up if you are back. We will get going with tidying our data. Awesome. All right. So to start, let's go ahead and open the new set of exercises. So again, that's going to be in your materials folder, 06 tidy, our markdown document. Go ahead and open that and run the setup chunk. I will do the same. All right. Okay. So now we're in this like middle ground between importing our data and really being able to visualize it and model it, where we have to clean it up a little. As I'm sure most of you have experienced, data rarely comes in like a nice clean format that's ready for us to use. And we often have to do some tidying. And that's what we're going to talk about this afternoon. We will probably not get through all of these slides today, since we only have a little over half an hour left, but that's fine. We'll finish them up tomorrow morning. So the principle that this is built around is tidy tools. And tidy tools, the guiding principles here are that functions are easiest to use when they are simple. So they do one thing, they do it well. They're composable, so they can be combined with other functions for multi-step operations. And they are smart, so they use R objects as input. And the tidy functions do this in a very specific way. So we're going to talk about the first two, simple and composable tidy tools. And so we've already seen this, right? So we were in dplyr, we saw filter, arrange, group by, select, mutate, and summarize. All of these functions do one thing. So if you want to filter, you're using the filter function. And they all do their one thing very well. These functions are also composable, right? So they can each be combined with the other functions as part of multi-step operations using the pipe. So the way that this is like working under the hood is that each function takes in a data frame as its first argument, and it returns a data frame. So that way it can be passed to the next step in the pipe. So that's tidy tools, but what we want to talk about is tidy data, which is going to be similar to the principles of tidy tools that we just talked about. So there's this good quote that is, data are not just numbers, they are numbers with a context. And so we need to understand the context in order to know like what is tidy and what is not tidy, because it may change depending on what the context is. So what are the variables in this data set? Right, so there are 4. There's the country, there's the year, there's the number of cases, and then there's the population. Right, so we have 4 variables, and they're all nicely lined up, 1 variable for each column. So what are the variables in this data set? So it's the same information. And so I would say that there are the same 4 variables. They're just organized in a different way. So we still have the country, we still have the year, we have the number of cases, and we have the population for each country. So we see the same information, but instead of being nice and tidy with 1 variable per column, we now have 2 variables that are kind of like smushed into 1 column, right? So this is not tidy because we don't have all of our variables in separate columns. So another quote, data comes in many formats, but R prefers just one, which is tidy data. And so we are going to talk about how to make your data tidy. So tidy data has 3 rules. And so a data set is tidy if each variable is in its own column, each case is in its own row, and each value is in its own cell. So those are the three rules that we're going to try and follow as we go through this. All right, so in your setup chunk that we ran, there was a data set called BP systolic. So what I want you to do is look at that data set and then think about what are the variables in that data set. All right, so what variables are people seeing in this data? So I see 3 variables. I see a subject, I see a time point, and I see a blood pressure reading. So that's what BP systolic is, your systolic blood pressure. So I see 3 variables, even though there are 4 columns here. So another way that you might arrange this data is like this, with 1 variable per column. So we have a subject ID, we have a time point, and we have the blood pressure reading at that time point. All right, so now using that BP systolic 2, which is like the tidier version of BP systolic. So with that data set and group by and summarize, we want to find the average systolic blood pressure for each subject. And then also find the last time point that each subject was measured. All right, so we'll take a couple minutes to work on that one. All right. So if we look at how we would do this, we can take our BP systolic 2, we group by subject ID, and then it's very easy to calculate the average systolic as just the mean of that systolic variable, and the last measurement is the max of the time. And so the BP systolic 2, because it's in that tidy format with one variable per column, it's easy to put it into this tidyverse framework. If we were trying to calculate these same measures on the non-tidy version, it'd be a lot harder, right? So the idea of tidy data is that it makes it easier to work with your data down the pipeline. So it takes a little bit of time to make it tidy, but it's going to be worth it in the long run. Right, I think this is my last quote. It's tidy data sets are all alike, but every messy data set is messy in its own way. And so we are going to learn some tools now that are going to help us unmessy our data. And to do this, we're going to use the tidyr package. And again, as has been the case for most of these, there is a chapter in R for Data Science called Tidy Data that's linked to here that talks a lot about tidy data and these tools that we're going to be discussing. So there are a few tidyr verbs or functions that we're going to be learning about. The first one is called pivot longer. This is going to take data that's spread across many columns and put it into fewer columns. So it's going to make your data frame or your tibble longer. Then the inverse of that is going to be pivot wider. So in our example earlier where we had multiple variables kind of squished into one column, we can spread that out across multiple columns and make our data wider, hence pivot wider. And then we can also separate columns. So if there are many pieces of information contained in one column, we can split that across multiple columns. And then the inverse of that is going to be unite. So we can put multiple columns together into one. All right, so we will start with pivot longer. And our toy data for practice is going to be this cases data, which doesn't have any particular meaning other than they are some numbers that I made up. And so we will start, if you want to throw some thoughts in the chat about what the variables are in this cases data set. So I think there are three. The first one is the country, right? And then we have the year. And then we also have the cases. So these three variables. Yeah, exactly. So these are the three variables that we want to get into a tidier format. So now I want you to take a few minutes and not in R, just like on a piece of scratch paper, or even just think about it for a couple minutes. I don't think we'll take the full 5 minutes, maybe just 2 or 3. Think about what a tidy version of this data set would look like. How would it be structured? Where would the values be? All right, so what might this look like if we were to sketch it out? So we have our original data, and we decided that there were 3 variables. So we have the country, the year, and then the number of cases, which I've called in here. And so as I think about this, um, we really take it like one row at a time. So we have France in 2011 has 7,000 cases. And then we have DE, which I think is Denmark, 5,800 cases, and the United States, 15,000 cases. And then we move to 2012, again, the number of cases for each of the country, and then finally 2013. So we end up with this much neater data frame where each variable is a single column. And the function that's going to do this for us in R is called pivot longer. So it's going to take this relatively wide data set and make it longer. So we start with our data that's over the 3 columns here, 2011, 2012, and 2013, and the cases. And we're going to make that into 2 columns, the year and the cases. So this is the argument of pivot longer called names2. So this is going to specify the new variable name for what was formerly the column name. So we're saying the column names are going to become year. And then values2 is going to specify the new variable name for what were formerly the spread out values. So we'll say these values are going to be going to a variable called n. And so the way this code looks is we have our cases data, and we want to pivot longer. We want to specify the columns that need to be pivoted, and that's in this case all of them except country. So we say minus country. The names to are year, and then the values to go to n. So again, the data we're reshaping, the columns that need to be pivoted, the name that the column names will go to, and then the name that the values will go to. So let's play with this one a little bit to get our hands on it. So what I want you to do is there's a data object called table4a. You can put that in your console to see what it looks like. I've printed it here for you. What I want you to do is use pivot longer to reorganize table 4a into 3 columns: country, year, and cases. So we'll take a few minutes to play with pivot longer on that one. Okay. So let's look at table 4A. So again, we have our countries, and then our years are spread across columns. So to get this in a tidy format, we'll use pivot longer. And the columns we want to pivot, again, are everything except country. We'll do minus country. We want our names. So our names are 1999 and 2000. We want to put those in a new variable called year. And we want to put our values into a new variable called in. So if we run that, oops, what did I do wrong? Oops, values, plural. And so then we get our nice tidy data set with country in one column, year in another column, and the number of cases are in the third column. Was everyone able to get pivot longer to work? Seeing yeses and thumbs up. Good, good. All right, so this will be the last thing that we talk about today. And that is the inverse of pivot longer, which is pivot wider. So the toy data we'll use for practice here is called pollution. And this is showing the number or cities and the amount of either large particulates of pollution and small particulates of pollution. And so what variables do we think are here? For the sake of time, I'm just going to kind of go through this one. So again, I think there are 3 variables, but not necessarily the 3 that are in the columns right now. I think there is one variable is city, and then I think there's large pollution, and then there's small pollution. So those are the 3 variables. And again, the context is gonna matter here. So this might be with size as one variable, might be tidy for some purposes and might not be tidy for others. So again, context is going to be important when deciding for yourself what tidy data is. And so again, I'm not going to make you guys draw this one out. We'll go through the example of what it would look like to make 3 columns here: city, large, and small. So if we start with our data set, again, we want 3 columns: city, large, and small. And again, we just go down the columns like we did last time. So we have New York with large is 23, so we drop that value in. Then New York small is 14, London large is 22, London small is 16, and then Beijing large and Beijing small round out our data set. And so then we have our 3 columns, city, large, and small, where each one is its own variable in our data set. And the function that's going to do that for us is pivot wider. And here we're taking 2 columns, size and amount, and we're going to spread those out across many columns. And so here we end up spreading it across 2 columns because there are only 2 values, large and small. But if we had large, small, and medium in our original data set over here, then we would also get a medium column. So however many levels are in this column is how many columns you'll get over here on the output. And so we kind of have the inverse of arguments as well. So instead of names to, we have names from. So our column names in our new data set are coming from the size column. And our values in our new data set are coming from the amount column. So where are the names coming from and where are the values coming from? And so this is what that code looks like. We start with our data set. and we say we want to pivot wider, our names are going to come from size and our values come from the amount. All right, and so this will be our last exercise today. We're going to look at now table 2. So if you hit table 2 in your console, this is what you will see. We have different countries and years with cases and population. We want to reorganize table 2 into 4 columns: country, year, cases, and population. So we will take a few minutes to do that, and then we'll talk about the solution before we wrap up today. Okay, so if we start with table 2, we want to spread cases and population out over multiple columns. So we'll use pivot wider. And again, our names are coming from the type column, and our values are coming from the count column. So we run that, we now have our 4 variables of country, year, cases, and population. So that is pivoting. There are, these were very straightforward examples, but there are many different ways that you might be pivoting and ways that your data might be organized. There is a great section in the tidyr website. So if you go to tidyr.tidyverse.org, there is an article about pivoting that has a ton of examples, including some pretty complicated examples of how you can tidy your data up using different combinations of pivot longer and pivot wider. So if you have some complicated data, I would recommend giving this article a read on the website. All right, so when we get back tomorrow morning, we will start with separate and unite. We have just a few slides left in this slide deck that we will wrap up. And then we will get into our first case study, which is going to tie everything together that we've been working on so far this week. So we'll have an analysis that we will be trying to replicate. Does anyone have any last minute thoughts or questions before we sign off for the night? No? All right. Well, I hope everyone has a good evening, and I will see you all again tomorrow morning at 9 o'clock Central Time. Have a great night.